let's look at binomial theorem. And it's theory or binomial expansion. It's a theory using Pascal's triangle. So when they say binomial expansion, what that means is we have two terms inside a set of brackets that we need to expand. And like in grade 11 or even 10, when I say the power of 2, we learn something called FOIL. We do the base times the base itself. But when it starts getting larger, when you have to do the base by itself 5 times over, it becomes extremely long and difficult to do. So there's actually a pattern we can use to solve this much quicker rather than using what they call FOIL or rainbow method over and over and over and over again. And what it is we can use Pascal's triangle. And Pascal's triangle is set up so that it's very simple to create. Okay? And the very first set of Pascal's triangle relates to binomial a and b to the power of 0. Okay? So actually the very first row would be considered the exponent 0. So with that being in mind, okay, what that means is before we get to the 5th exponent, that means we'd have to be on the 6th row. Okay, so right now this is the first row. So our second row then consists of 1 and 1, okay, and that would be a plus b to the power of 1, okay. Our third row would be 1, and then we add the two terms. So we add everything in the middle. So 1 plus 1 is 2, and 1 always stays out on the outside. That's why it creates that triangle look. This would be a plus b to the power of 2. And what these are doing is they're creating the coefficients that are going to go in front of our expansion. Okay, so the fourth row would be 1. We add these two together, 3, 3, 1. This would be a plus b to the power of 3. Okay, we got to get to the 5th, right? Mm-hmm. The 5th row is 1, 4, 6, 4, 1. That's a plus b to the power of 4. So again, we're always just adding values in between. And then the 6th row is when we're actually looking at the power of 5, and that would be 1, always 1's on the outside. 1 and 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and 1 again. And this would be a plus b to the power of 5, okay? So what this is going to tell us how many terms there are when we expand this. So there's going to be 1, 2, 3, 4, 5, 6. There's going to be 6 terms when we're at the power of 5, and we're in the 6th row. These are going to be the coefficients that we're going to multiply our a and b term by. So we'll call this our a term, and we'll call this our b term in the brackets, okay? There's another way to find all of Pascal's triangle using combinations. Have you guys ever talked about that at all? Find the exact values? For this thing, it's not imperative that we learn it, but the idea is that the first row would be 0, combination 0. Next one would be 1C0, 1C1. Okay, so depending on what row you're in, you can find it. So this would be 1, 2, 3, 4, 5. So in this row, we'd have 5C0. 5C1, 5C2, 5C3, 5C4, and then 5C5. And when you put those combinations in a calculator, it'll give us those exact values, okay? But besides the point. So let's go into our expansion. These are each of the coefficients. So the very first coefficient is going to be the number 1, okay? And we're going to have the letter a to the power of whatever the exponent is, 5, okay? And b is technically to the power of 0, which means I don't have to write it in, but I'm going to. So instead of instantly substituting these in, I'm going to build our row using just a's and b's, and then we're going to substitute our a and b values in and solve, okay? So our first coefficient is 1. Then we'll add our next coefficient is 5. But since we're 1 over, this now becomes a4, so we subtract 1 from a, but we increase our exponent on our b, so b1, right? The next value is 10. Do you know what the a term will be?
3.
Yeah.
Wait.
So we go 5, 4, 3, yeah, and then the b term will be 2. The next coefficient.
Wait, if we're decreasing the a term,
yeah,
wouldn't it be 4?
We did 4 right here. We had A5,
okay,
A4, yeah, A3. So the next one after 3, we'd have A2, and then because we're increasing B, 1, 2, 3, this would be B3, okay? And we continue that. So plus 5, A1, sorry, I forgot we're going up or down, and B4, and then finally the very last term is plus coefficient 1 times a to the power of 0, which isn't going to be important, but that's okay, and then B5. So this is the setup for the rows. We always start with the highest exponent and the first letter, we called it our a, and we just kind of count downwards, and then we multiply it by the second term, and we cut upwards on their exponent. So remember that a was equal to above negative 6x squared, and b was equal to x over 3. These would be considered difficult terms to expand. But once we've built this formula here, it's just substituting numbers in. So our next row, we have 1 times whatever our a term is. So a is negative, we'll write it in, negative 6x squared to the power of 5. Okay. The b term is unimportant. B to the power of 0 is 1. So I've already got my first term. I'm going to have to expand that and figure out what that is, but we can do that next. We'll just fill in our spots. Next one's going to be 5 times, again, negative 6x squared, but this time to the power of 4. And our b term to the power of 1 times x over 3 to the power of 1. And we're going to continue that pattern. So plus 10 negative 6x squared to the power of 3. So even though it has an exponent on the inside, that just replaces the a term. Our exponent on the outside still is important. Right? So we always have to make sure we have that. Our b term here is just x over 3 to the exponent of 2. And then plus 10 negative 6. I'm going to try to squeeze it on squared. Squared. B is x over 3 to the power of 3 plus 5 times negative 6x squared. Our b term is x over 3 to the power of 4. And then finally plus, I can kind of squeeze it in. Remember the a term is unimportant here because it's a to the power of 0, which is 1. And it's just going to be x over 3 to the power of 5. Okay, we fit it in. So now we go about, think of each of these. Like this is one term, this is a term, this is a term. And like we said, we're going to have 6 separate terms. So we're going to equate each of them. 1 times anything is going to be that number, so that's going to be unimportant. And this is negative 6x squared times negative 6x squared times negative, so 5 times over. So one way you could do this is a power of a power rule for the variable. So what we do there is we multiply the 2 exponents, so that becomes x to the power of 10. But we still have to put negative 6 to the power of 5. And that's going to be a relatively big number, so we're going to use a calculator here. And we're going to have our negative 6, I don't know if I have to put it in brackets here, I might. Negative 6 to the power of, where's my powers? There it is. Power of 5. Okay, so this first term is actually going to be a negative. Negative 7,776. So negative 7,776 and x to the power of 10. Okay, so there's our first term. We've checked it off. Our next term. This is where it gets a little trickier. Okay? This 5 is going to be multiplied by negative 6 times the power of 4, whatever that is. And then we're going to have to multiply by this. So this is where it gets very, very complex when we have these values here. So I'm going to do one of them on the side, and then I'm going to show you how we can do it a little quicker once we get this pattern. So it's 5 times negative 6x squared to the power of 4 times x over 3 to the power of 1. I've got the wrong font. There we go. Okay. First, we've got to find out our negative 6. There we go. So we know that we're going to take our negative 6, but this time, we're going to make it to the power of 4. So our value is 1,296. Okay. So that would still be 5 times 1,000, I already forgot, 296?
Yeah.
296. Our variable, okay, we're going to keep these all separate. So 5 is a number. 1,296 is technically a number. X to the power of 2 times 4 is 2 times 4 is 8. So x to the power of 8, that's a value. Okay, and it'll be probably easiest here if we kind of actually split this. And I can split these into 2 terms. So think of it like if I multiplied 1 over x times, x over 1 times 1 over 3, I would get x over 3. Okay, so that's what this is. I'm going to use this instead. I'm going to split them up, decompose them, just so I can start to see what a like term is and what isn't, okay? So that's going to be times x over 1, okay? And I don't really need the over 1, times 1 over 3. So now what we can do is kind of lump our like terms together. We have our constants we can multiply, and we have our variables we can multiply, okay? Now we multiply the variables, actually let's do the constants first. When you multiply by a third, it's the same as dividing by 3. So I'm going to multiply these 2 values and then divide by 3. So 5 times our value, okay, divided by 3 equals 2160. Okay, so our coefficient is 2160. And then this is the same as just x to the power of 8 times x to the power of 1. And we just add the exponents. It becomes x to the power of 9. Okay, so now this is one term, which is 2,100. and 60 x to the power of 9. Okay? And you're going to repeat that process for each of these, going through it over and over and over again. Okay? So that part in itself is tricky. But this is the idea for expanding it. So you would kind of go through the rest of them there. Okay? Let's see. Carried this all the way out to the end. These are your 6 coefficients, and your exponents count from 10 all the way down.